welcome everyone to tonight's Ivan Hour, first Ivan Hour of ENC 2023. Welcome to the joint booth of Q1 Instruments, MR Resources, and the Ivan NMR Users Group. Glad everyone is here with us tonight. Very, very interesting talk by, dare I say, a luminary amateur astronomer and NMR guy we all know and love, Ron Crouch. Anyways, Q1 Instruments, glad to sponsor this. MR Resources, glad to sponsor this. After the meeting, we're going to have our first raffle for the evening. And 3 raffles tonight, right after the meeting, roughly 9 o'clock. Have another one at 9:30 and another one at 10. I don't think we can give the order of prizes right now, but they're pretty cool tonight. $50 Visa gift card. Yeah, that's okay. But laser engraved, solid wood periodic table cutting board.
Yeah.
But something really cool is there's the cutting board in the back. But something really cool, brand new for this year, is logo longboard. And the winner is welcome to take it out on the boardwalk and show us their skills. Anyway, let's get going with things tonight, and I'll turn it over to Dave to make the introduction.
Okay, great. Well, last year Ron spoke at the Ivan Hour, and Ron, in addition to being a great NMR spectroscopist known to most of the NMR community, he is also an amateur astronomer with some really cool telescopes. And and last year he gave an Ivan Hour, and it was so great that we wanted to do it again. And this year he's going to talk about some mysterious Frau Newt. And also about Webb.
Yeah.
And and so with that introduction, I'll give things to Ron.
Well, it's great to be here. It's a real honor. Thank you. I never thought there would be a season 2, you know, and so if we can shift the display here. All right. Oh, there it is. No, the down arrow. Look at that. Oh, test pattern, test pattern, test pattern. Okay. What are we going to talk about? We're going to talk about the art of imaging with astronomy. So anywhere you look in the cosmos, there's something to be seen. And the deeper you look, the more you see. It's astounding, and we'll get into that a little later. So what this is an image of a galaxy called the Cigar Galaxy. It's not that far away from us. It's only 40 million light years. So this is taken with a 4-inch telescope, is it. And the red jets you see are basically hydrogen gas that's being expelled from just some sort of a cataclysmic explosion that's going on. So I've been at it a long time. I started when I was just a kid, just a little tiny kid, and they called me Lefty at the time, but imaging does not involve looking to a telescope, okay? It means that you put a camera chip sensor behind the optics, and you record it in lots of time. We're going to look at little details. So when you think about it, scale-wise, this is what you see with a very modest sensor, only 19 by 13 millimeter, with a telescope that's an 8-inch f5, it's that big around and that long, at 950 millimeters. So that's what the moon looks like. But if you point it somewhere else for a long time, that's the same field of view. And so it's quickly apparent that you can look in random places, and anywhere you look, you see something interesting. So here's a collection of galaxies. There's probably 80 galaxies visible in this field if you do some pixel peeping, okay? So that's what the amateur astronomy is. What we all know is that the Earth turns. How fast does it turns, right? 24 hours in a day, 360 degrees in a circle, so that's 15 degrees in an hour. So that's 15 arc minutes in a minute and 15 arc seconds in a second. Well, that's 40 seconds of exposure with no tracking on. So many of these exposures accumulate over many, many hours. So they're done over a lot of time. So what are we looking at? This is NMR, but just at a different frequency. So it's the electromagnetic spectrum. So if you take a look here, well, we can't see it, but in the middle is what our eyes see in the electromagnetic spectrum. A very narrow band, centered in red, green, blue. There's not a lot eyes can see outside of it. Now, if we were owls, we would see pretty far into the ultraviolet because they use that to hunt at night to track little rodents that go along the grass, and they piddle as they walk, and it glows in UV, and so it makes it visible. Some dogs and stuff are visible a bit into the infrared, but not us, so we only see there. So how do we image? You can put a regular DSLR camera onto a telescope and you can record in color directly, but there are advantages to having a camera that is just monochrome, it's just black and white, and you use red, green, blue filters. And then when you're done acquiring them, you map directly. What does this do? It gives you about a factor of 3 gain in sensitivity by not using a color chip, and it also gives you a lot more resolution. For the same pixels in a color chip, you're taking 4 of them and you're bending them together to combine to make the color. But in a mono camera, it's only 1, so your resolution is much higher. So you combine all of those, and if we look in the previous, I sort of have a little box in the one labeled luminance there. If you take that little box and the combined thing and you expand it, that's kind of the detail of what you see in the color. So the color is synthetic. We're looking at with a monochrome camera and we're mapping it to, in our case, red, green, blue. Why? Because that's what our eyes see, okay? There's other things. Here I've roughly overlaid on the top red, green, and blue. And the small filters underneath are narrowband bandpass filters. Each of these bands might be, in this case, 3 nanometers wide. And so they are tuned, what is red, green, and blue are sulfur 2, hydrogen alpha, and oxygen 3. These are specific wavelengths that show you the chemistry in objects in the sky. So Hubble telescope made this famous because they could suddenly look at different nebula and directly image in high resolution and understand the chemistry. So this is an example of a narrowband image, false color mapped. So here the blue hydrogen, oxygen 3 is mapped to blue, sulfur to red, and hydrogen alpha to green, and a little palette shifting. So this is about a 20-hour exposure of an area in somewhere, and I don't remember any of the details. But what's nice about it is you suddenly pick out a lot of detail because of the narrow band. It's not a lot of broadening of things. Now let's return to the infrared electromagnetic spectrum. And boxed in, you see infrared. And when we think about the JWST, or the James Webb Space Telescope, it's an infrared observatory. It does not look at optical bands at all. It's only infrared, and why is this? And that is because the mission is to look, one part of the mission is to look far back in time. And the thing is that the further back we go, what we seem to know is true is the universe is expanding. And as such, the wavelengths are stretched longer and longer. And by the time you get back to the points in time where the Webb is designed to look, there is no visible light left. It's all stretched into the infrared or lower in frequency. So these are the telescopes that I use at home. This is Timmy, a nice little telescope. It's an 80 millimeter f5. That's Timmy on the mount. This is Newt. It's the largest telescope. It's an 8-inch f5, so it's that big around and about that long, and it weighs about 50 pounds, and it sits there on the mount. Now, the newest addition is Frau Newt. And his name Frau Newt, it's a smaller version of the other. It's a 6-inch f3.9. So what's the big deal? It's that optics work by f ratio. So what you see in a telescope as a function of diameter is the bigger the diameter, the more stars you will see. But stars cannot be magnified. They are point sources. And the irony is, the bigger you make the telescope, the smaller the stars get. They are not things that can be magnified at all. But an extended object, like a galaxy or a nebula, it only is F ratio. So f3.9 with a 6-inch telescope will gather light twice as fast as a larger diameter telescope at f5 or 6. So you can save a lot of time in imaging, and you gain field of view. So historically, these are some slides. We have refractors. That kind of came first. That was a nice idea. And they expand up nice, and now you kind of look at it and you go, well, this is heroic. But by the time you got to a 40-inch refractor, the problem was gravity distorted the lens, and you couldn't maintain the shape. And so you take a look at that same telescope back in the day, like 1890 or something, you see it's a rather unwieldy item. Around 1660, Isaac Newton came up with the idea for a reflecting telescope, a Newtonian. And what's nice about it is it's very, very simple. We have a mirror surface in the back, and what's dramatic about that is that it's supported in the back so gravity won't distort it. So you can make it much, much larger than you could ever imagine making a refracting telescope. So here's a picture of, on the left is the Hooke telescope. That's a 100-inch telescope there in blue. And on the right is Mount Palomar, just down the road, which is a 200-inch telescope, or 17-odd feet in diameter, and you can kind of get a sense of the size of it. So back in the 1930s, when this thing was manufactured, it was a bit of a deal, because first off, making a 200-inch quartz disc was almost impossible. It took many years to cast the disc. And then when they were done, they needed to get it to Pasadena. It took 4 months to route a railroad route to move the disc by train from Ithaca, New York to Pasadena, because it couldn't go through any tunnels, and it had to have clearance to get over, under bridges and stuff. And there were no computers to map it. So it took 4 months just to figure out the route. So eventually they trucked it up the hill in a truck, and they put it together. So this is the Palomar. This was an enormous shift in our ability to study cosmology, because of its size at 200 inches, it gathered so much light that you could do spectroscopy, which is the real key in research telescopes, on point sources in stars and in galaxy, and understand what is the chemistry of this. So in other words, you point it at a star and you do spectroscopy, and you basically see the barcode of what are the atoms that are involved. Now, the mass of that telescope was 500 tons. And it was so well made that you could put a milk jug on one of the arms you see on the side, on the image on the right there, and it would turn if the gears weren't involved. That's how precise this thing was. Now, fast forward half a century. The aliens visit, they tell us a lot of cool information, and next thing you know, bang, we're not delivering telescopes by train and truck, we're delivering them by rocket. So here's Hubble. So Hubble weighs 25,000 pounds. It's a little under 8 feet. It's been in orbit for a long time, and it's completely changed our view. But suddenly, last year before, this is a mock-up of the James Webb telescope with a small part of the team that's launched. And to understand this, the mirror part that you're looking at is beryllium, coated in gold, because it's an infrared telescope, and you need that to reflect the infrared. It's over 20 feet in diameter. So there it sits. It's in orbit, and we'll look a little bit about this. It's basically larger than Palomar, and is now in orbit, and it's not orbiting the Earth, okay? Let's look at the details and the mission goal. The mission goals: search for the first galaxy or luminous objects that were at sort of the dawn of time, taking us back before what Hubble could see. Determine how the galaxies first formed. observe the formation of stars, the very first stars, understand the chemistry and where are they. From the chemistry that you observe, shifted to the infrared, they know how far away it is. So they can go back and understand this is 11 billion light years, that kind of thing. So, and also measure physical and chemical properties of exoplanets. This is quite a shocking thing, and so it's quite capable of doing this in the infrared. So this sort of graphically shows, these are from the Webb thing, the area where it's trying to understand are the first galaxies and the time just up to the first galaxies, okay? This is the scope. I think that the little flap on the side I labeled, that's a stabilization flap. And it uses the solar wind as a stabilization. It's sailing in its orbit, and that's using the solar wind. Sadly, it's only adjustable from Earth. It's not adjustable in orbit. So they got it at just the right angle before they launched. They figured it out. So the sun shield, as you see, is a bunch of layers of mylar. It's the size of a tennis court. So think of that, and let's put it in orbit. And where do we put it? On the left is where Hubble is orbiting the Earth, low Earth orbit. So basically, the periodicity of an Earth orbit, roughly 90 minutes, means that you've really got not much more than 45 minutes of time on any particular project before it shifts to the other side. Then you got to wait and start it again later. This is orbiting at a Lagrange point, and I don't think this is going to show on the screen. So we're looking at the Earth with the moon orbiting it, and way beyond it is where Webb sits. And so the orbit is really interesting. It's a little point in space, as is diagrammed here, and it's doing its own little tiny orbit around this particular point, and it's moving as an ensemble around the sun as the Earth does. So it's in constant position, and it's sitting there. And so that's where it sits, 1.3 million kilometers from Earth, in a very precise location. So its availability is 24/7. Those of us who do NMR and like cold things, the passive temperature of the sensors in Webb are 25 degrees Kelvin. They're the passive sensors. The active sensors are 5 degrees Kelvin. Okay, so that's where they sit. It's cold there. You don't need anything at all. If you're sheltered from the sun, if it was exposed to the sun, it could be 400 degrees Fahrenheit. So a little more about telescopes. This is something from last year. These are two fields of view for two of my telescopes. The big, larger one, red, is TEMI, the 8-inch f5, the 80 millimeter scope, and then the blue one is the same imaging system, but with Newt, which is at almost a meter of focal length. So you see that the bigger the telescope and the longer the focal length, the smaller the part of the sky you can see. That's just the way it is. There's no way around it. So if we take a look here with an 80 millimeter f5 pointing somewhere out near Taurus, we see a whole lot of galaxies. There's 3 that are pretty obvious that jump right out at it, but there's many, many more in the image. So if we change the telescope to a 1 meter focal length and point it, that's now what you see. I just pointed at one of them. And so now you're beginning to see a whole lot more detail. It's hard to tell, but you can see trails of galaxies from collisions and things that went through here. So this is done from a backyard in, maybe this one was in Colorado, I don't even remember, probably maybe Texas, and it's maybe 20 hours of exposure or something like that. Well, we'll get into what Webb does in a moment. What is amateur astronomy? It's basically waiting for the stars. Okay, that's really what we do. We wait for the stars to appear, and often that's what you see. So I've got my phone here, and we'll go here, and I'll go to VNC, and I'll connect to the NUC, and look, and lo and behold, the observatory in the backyard is running. So that's the telescope in Texas, and it's happily running right along. So it doesn't matter where you are physically, you can run it in today's world. I mean, if you can run Webb from 1.3 million miles away, I can surely run my telescope in my backyard. There's no doubt about it. So thinking about that, there's another telescope in the yard. This is called the Mouse Dome. It's a little tiny dome. It's about that big around. It's got a little all-sky camera in it. And so I can look into it at any time, and I can see, is it cloudy, for instance, right? So we see on the left cloudy, and on the right we see clear, okay? So you can know what are the observing situations. That's the observatory itself, weather systems, blah, blah, blah. Now, why bother? This is my favorite slide of the whole thing because I have nothing to do with it. This is Benjamin May's, and that is the tragedy of life doesn't lie in not reaching your goal. The tragedy lies in having no goal to reach. It isn't a calamity to die with dreams unfulfilled, but it is a calamity not to dream. And it's no disgrace to not reach the stars, but it is a disgrace to have no stars to reach for. So this hobby is about the fiddle factor. Okay? That's what it's about. It's about making it work. So this is another, object. I believe Timmy did this some years ago, and you just look at the variety and the complexity of what's out there. This is in narrowband light. That's called the jellyfish nebula, the dominant one there, narrowband light. Last year I assigned homework. This was the must-read thing, where there'll be a test later to see who read. But I highly recommend Timothy Ferris's Coming of Age in the Milky Way, because it gives a really good overview. Now, this is something else that I'll enter again. As a species, we've been at this a long time. And you might ask yourself, when did we learn cool things? So in the 1300s in India, trigonometric tables for using sine waves by infinite thing were derived for one reason, was to determine how far away are we from the sun. So if you look at the geometry and the trigonometry of this, and imagine in this image here, a quarter moon instead, you look, by simple trigonometry and knowing sine and cosine, you can calculate relative distances between the Earth, moon, and sun. You can't get absolute distances, but you can get relative distances. So in the 1300s in India, it was determined that the sun is 400 times further away from the Earth than the moon. That is exactly right. So, gravity. Great lyrics. Something always brings me back to you. It never takes too long. You hold me without touch. You keep me without chain. Sarah Bareilles, what a poet. But that's the story of gravity. And you look at gravity. When Newton came up with the equation for gravitational attraction, this was his equation. It's very simple. It's the product of the two masses times a gravitational constant, which he had no clue what it was, with the inverse square of the radius of the separations between it. So you go forward a couple of hundred years, and a minister, they literally weighed a mountain next to his house. They didn't weigh the Matterhorn. That's just a nice picture. But there was a nice mountain beside his home, and he made a big copper ball and suspended it from the ceiling. And he measured how much the copper ball was deflected towards the mountain. And by making that measurement with some sort of a bizarre calculation, he came up with the value of the gravitational constant. It is correct to 3 decimal places. Okay? So as a species, cosmology marches on, right? So it doesn't matter what your technology is, no matter where you look, it gets deeper and deeper the more you learn. Well, let's look. There's a galaxy that's close. It's 50 million light years away, okay? And that's a look. And so I can look at it with an 8-inch telescope and image it, and I can go, gee, that's pretty cool, and I can show it to you at the actual pixels. But literally, that's as close as I can get with my technology. We can see lots of little nebulae and other little galaxies in there, and it's kind of fun, but it's basically a pretty picture, and there's really no science to be had here, okay? We can look at larger galaxies, and we can think, yeah, we can see more, okay? And we can look at still larger galaxies with smaller telescopes, and we see more. So this is the gravitational monster that we're racing towards at 250,000 miles an hour. And we'll get there in about 2 billion years, okay? That's the scale of it. We have nearby stuff. This is the next spiral arm out. 2,000 light years. The Horsehead, very, very famous thing. And the red gas is hydrogen that is glowing. That's what that is, from the stars, okay? We have galaxies that are edge-on, okay? There are over 80 galaxies in this image, and you can only see maybe 3 at this scale. So it all depends on what you see is what is our orientation. So we take a look here with a small telescope at that little fuzzy patch up in the upper left. That's a galaxy, and I can zoom in on it and look and say, well, that looks pretty cool. That's kind of nice. But you take a look at it with Hubble, and that's what you see. The shocking thing is, those are actually recognizable of one and the other. You can tell they're the same object, but you certainly cannot tell from the detail of what's going on. So this is what Hubble gave us, was the ability to see these objects in absolute splendor, and not only to see them, to focus a spectrograph at individual objects inside of this galaxy and determine its chemistry. So we take the same token and we look at a supernova remnant, the Crab Nebula. On the left is Newt from my backyard. On the right is Hubble. Now, James Webb. It's an infrared observatory. Again, why? What it's designed to look at is all shifted from visible to infrared. So when they do images that we see, they are mapped to red, green, blue, so our eyes can receive them, okay? But they're still perfectly valid. But the spectrographs are the key for the science of what's going on. So this is a spectrum, an infrared spectrum from James Webb at a young star that is just forming near a young star. And so you can take a look at an IR and read the barcode. You see CO2, water, hydrogen cyanide, CO2, carbon monoxide. These are all chemicals that you can get the identity and get relative amounts of them. So that's the sort of thing you do. This is the science that they're interested in, not the pretty pictures, okay? Cassiopeia A is a supernova remnant. Through Newt, this is nothing but a fuzzy patch. Nothing but a fuzzy patch. So this is Webb in infrared. This is a chaotic supernova remnant. Now, Webb's deep field. I asked myself, do I feel guilty that as we're sitting here, I'm trying to add up to 60 hours of exposure on an image that I got to 15 hours and I can see is worth going more to make a difference. Just like in MR, you want to double the signal noise, you got to go 4 times the time, right? There's no route about it. Or you get a bigger telescope or a faster ratio. So this image is 250 hours with a 20-foot telescope orbiting 1.3 million miles on the other side of the moon from us. Every speck in this image, I mean, the stars show as you see the diffraction spikes on the bright stars, but all of the every little tiny speck you see in that image is a galaxy. And the deeper you go into this image, the more galaxies you see. But the astounding thing is that with Webb, it doesn't matter where they point in the sky. This is what they see. This is a very tiny patch of the sky. And there's, I believe they counted something like 19,000 galaxies here. And so it's quite an astounding thing from such a perch. Now, what happens if you point a telescope at something you can see? So this is a star that I can see with my eye, right? And this is Frau Newt, a 3-minute exposure on Frau Newt, and you see what happens. All the little stars, is not that they're smaller, it's just that they're fainter, right? So they're all kind of washed out and big. So you can kind of get a sense, and you were looking into the observatory at that time. But Stephan's quintet is a grouping of galaxies in the autumn sky. On the left is the James Webb infrared image. On the right is something that Newt did of the same field a few years ago. And you go like, wow, as an amateur astronomer, I'm encouraged. It makes me think I can do better now. I think instead of 4 hours, what would happen if I use 40 hours, right? So it's the fiddle factor, you keep going. Webb again, a common object in the southern hemisphere, but in unprecedented detail, the Cartwheel Galaxy with Webb. Just an astounding image. And again, to me, the beauty of this image is obviously the detail in the large objects, but to me, it's look at the background around it, and what do you see? Galaxy, 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 everywhere. Just, there's billions, billions. Made famous by the Hubble, the pillars of creation. This is with Webb in infrared, and it's mapped. So it's really unprecedented detail. This is the same data processed a different way. Infrared is mapped, so it looks kind of ghostly. So on the right, on the inset, is Newt from my backyard, pointing at the same object. And you can kind of see, the pillar area, looks like a little tiny eagle up there. You can get a sense that, well, yes, we are pointing at the same thing. But for Webb, it's not about the pretty picture. It's about the fact that they can look at individual stars and pockets in this and do spectroscopy and understand what's going on. This is the Hourglass Nebula from Webb. Now, you might be asking yourself, well, gosh, Ron, why didn't you point Frau Newt at the same stuff that Webb is doing? And the reason is, Webb is in orbit in sync with the Earth. And it's out, and where Webb is looking now, we will be able to see 6 months from now. So 6 months from now, this stuff is all there for me to see, but not now. It's up in the middle of the day, right? And so 6 months from now, these things will become more valuable. Now, on the left here is an image from Hubble. On the right is Webb, and of the same little boxed-in box, but it's processed to show you the actual relative motions of interacting galaxies and the velocities that they're moving with respect to each other. So this is the kind of unprecedented detail we can get from distant things. This is a galactic collision done with Webb, 2 galaxies, they run together. Whoop, wrong button. That's a galactic collision with Newt. This is a much bigger one. So that's a nice spiral galaxy that's been run through with the other. And, there's a lot of detail to be seen. Relative sizes, the other object is roughly the size of the core of this, nothing more. So if we point at the brightest nebula near us, with Stella, who's no longer with me, we see the Orion Nebula. It's one of the few things you can see with your naked eye. It's really, really bright. Webb looks at it in a different way. Webb looks at the Orion Nebula, and it's looking at the chemistry that's involved. It's looking at pockets of where stars are being formed. And a little inset up here on the top right, you see a little oval drawn, and that says the orbit of Neptune. That gives you a sense of the physical size and scale of these little tiny objects that are there. So on the left is Hubble, pointing at a little dead star. This is the fate of our sun. Our sun, this is what our sun will become. Exactly. On the right is an amateur astronomer imaged the same thing with about a 20-inch telescope from somewhere in the Sierra Nevada. This is the same object with Webb. It's the same data, each image. It's just processed differently, the mapping of the infrared. And so now we can suddenly see all kinds of detail, all kinds of chemistry. On the right is a similar object that's a half again larger than the last one with Webb. On the left is the same image with Newt. So we can see we're looking at the same thing, but it's a whole different matter. This is the core of a galaxy looked at with Webb. It's looking at it and it's literally seeing the bones of this galaxy by focusing in infrared. It cuts through all of the dust. And we can see things that optically would never appear. So Webb is designed also to look at planets and our own planets. So this is a view of Neptune with that. It's something that's not been seen since Voyager went by, right? The Tarantula Nebula with James Webb. Again, a southern sky masterpiece. All of the incredible chemistry and things that are going on in it. Top left is a galaxy in GC 1433. This would be a nice object for Newt. This is done with like a 15-inch telescope on the top left, and that's an image of it with Webb. And we're just looking at the core middle part, and you see the unprecedented detail. But Webb does lots of things. This is a Wolf-Raynaud star that's out there, and on the right is a similar object done with Newt. But the object I'm looking at is 30 times larger than the one on the left, right? So I can record it nicely. It's called the Crescent Nebula, if you will. So it's a very unusual star in the center. It has crazy radiation patterns that are going on. Now, exoplanets. This is another one of Webb's items to do. So if we take a look at this star system, and the figure shows us that what we're looking at is like our inner solar system kind of blown up to show you this star system around this star TRAPPIST, is what it's called. Webb measured the temperature of the innermost planet with its infrared. And so we know that the surface of that planet is, what is it, 500 and some degrees Fahrenheit. I mean, roughly 450 degrees Fahrenheit is the surface. What they know from this is that it has no atmosphere, because they know if it had an atmosphere, the heat would be evenly distributed and it would be a little bit cooler. So they know this planet has no atmosphere. If it had atmosphere, they could do spectroscopy on it. Okay, so this is where TRAPPIST sits in the sky chart. It's in Aquarius, so it'll be nicely placed in August for us. So how would I observe it? Okay, I would say, oh, that's where it is. I would go to my observatory and I would enter its right ascension and declination and what I want to do with it, and I put it in the database, and when it gets up in the sky, it'll image it at the time, so you can make your decision now for what's happening. But there's a wonder of things in the universe. We're looking at very cool things. So there's blue things. They are really reflection. What it means is it's a star that's bright and it's causing gas to reflect and glow. This is M87, which is a very small reflection nebula near Orion, done with Newt. This is a very deep image just in hydrogen alpha light. And if you look closely, you might see what you perceive as a dragon in there, just the filaments of a dragon that are going out there. So there's objects like this all over the place. I could make this image color and make it red, but somehow it's a little more interesting in monochrome to me to see it in that way. You can see the detail. But if you look and you do hydrogen alpha and oxygen 3 and you go very, very deep, this is about 50 hours of total exposure, what you see is a bizarre oxygen cylinder, twisted cylinder object that's floating through this red glow, okay? So it's just, our universe is full of bizarre items. There's no question about it. But when it comes right down to it, it's about chemistry. And so we can do narrowband chemistry and map sulfur, oxygen or hydrogen, if we're using filters to that, to different colors, and we can look at objects like this and we can understand the chemistry of what's going on. So you see there's an awful lot of oxygen involved in this nebula there. This is a star that has died. The central star, you still see it, and you see a gaseous cloud that's a sphere that's around it. And there are thousands and thousands of these if you look. Here's another one. You can look through this and you actually can see galaxies through the backside of it visually on this. So this is, again, with a small telescope. When these things become apparent, and like Webb points out them, it's going to be quite fascinating to see what comes up. So we have objects in narrowband light that are any color you can imagine. Just a host of bizarre chemistry. This is called the Lion Nebula, if you will. And finally, my favorite kinds of objects in the sky are literally small galaxies and things like this. So this is a little patch of galaxies, and you see near ones and far ones, and all in families. But but you always come back to narrowband light for the ability to map and get the dramatic, pretty blues and things like that, and the chemistry. I started with this object, this image, showing how red, green, blue looks. So this is another dramatic object that is in the sky. And the thing that's really astounding is that even with binoculars, there's nothing in this image you would see. Nothing. It's all way, way below it. So we're looking here at about 25 hours of exposure with a F5 optical system. Similar here, called the Angel Nebula. All kinds of beautiful things. The difficult thing in processing this image is that there's so many stars. They would completely overwhelm the nebula and you wouldn't see anything. And so the tendency is how do you suppress the stars but let them still remain and all. So there's an artistic side. And finally, another narrowband object that's just showing all of the amazing chemistry that's all around us. So these things are anywhere you look, okay? You can point randomly in the sky and you will find things like that. So what's Frau Newt doing now? This is 14 hours of data on a chain of galaxies. It's called Markarian's chain, okay? So every one of those bright things is a chain. You see the little call out, there's a small little galaxy that's a spiral galaxy that I expanded and is on the right-hand side. And if you look into that expansion, and you start pixel peeping, what you'll see is that there are 35 or more galaxies in that small little patch that are around it. So the object of the game is, right now, when the observatory is working, to try to push this out to 80 hours. And the point of that is that now I will have my own deep field. So in other words, we'll be able to see these large galaxies, but the small ones will now be above the noise. And you'll be able to look and see very, very deep. Finally, as the last image to show you, that's a good time, I thought I would show you our galaxy. And this is what our galaxy looks like from afar. So this is NGC 2336. It's hiding way in the north. It's not that far from the North Star. This is about 18 hours of exposure at a meter focal length, and the galaxy up at the top we see is a very pretty spiral galaxy with interlocking arms, and its structure is almost the same as our Milky Way, and it's the same size as our Milky Way. That's the sobering thought. It's about 100 million light years, it's about 100,000 light years in diameter, and its distance is 100 million light years away from us. So if you lived there and look back at us, that's what you would see. Okay? So I think that's really a good place to stop. And thank you all for coming. Yeah.
Ron, just incredible. You know, not entirely unlike in certain respects some of the things that we do with NMR.
Yeah.
Yeah. And what do you guys think? This is what Ivan Hour series is all about. We've got a great one coming up again tomorrow night. Very importantly, I want to point out that Ron is this year's winner of the Ivan Founders Award. Just give it out on Saturday, a couple of days ago. I hope you guys enjoy this, and I know you want to see a drawing now. I guess we will do that. So 3 drawings tonight. Now, what is about the 9 o'clock hour? One coming up at 9:30, another at 10. $50 gift card. Shelley, could you hold up the now famous laser engraved wood periodic table? Kind of cool. But the good stuff is the kind of the longboard in the back, new for this year. We're going to do a $50 gift card right now. Sharon, what color is the ticket for this hour? Who does not have a green ticket? Raise your hands. And by the way, we invite everyone to stick around between now and 9:30 for the next drawing. Could be the cutting board, could be the skateboard. I don't know. We'll see. But in that half hour, please do speak with the folks at Q1 Instruments. A very, very good line of 400, 500, and 600 NMR systems. I dare say as good as the competition at much more attractive price. And also, please speak with the MR Resources folks. Service and service contracts, I'll make a very bold statement, as good or better, and certainly more timely than maybe what you're getting from others. But anyways, let's get the tickets passed out. Who else needs a ticket? Could I ask Ann to come up and make the drawing, please? Sharon, Ann just made a very good point. Could you just check, swing the reason we shut the door is a little bit loud next door. That's all well and good, but maybe anyone else? Okay, let's make a drawing for the $50 card. Ann, if you would, please.
Last 4 numbers is 8150.
Nice. Okay. Very cool. Please see Shelley over in the corner here, and she will set you up for a $50 gift card. Like I say, next drawing in 35 minutes. Don't be afraid to stick around. Talk with the Q1 folks, talk with the MR folks, and in any event, we'll hopefully see you and others at 9:30.